This video focuses on the part of our unit that we like to refer to as formula analysis. This video will specifically refresh us on percent composition and problems where we are asked to find the empirical and or the molecular formula. So first, percent composition. Percent composition is a mass ratio unless otherwise told. So if you are asked to find the mass percentage of composition of a compound, it will be the mass contribution of the element, usually in grams, divided by the formula mass of the compound, usually in grams. You could both be in kilograms, both be in milligrams. You are multiplying by 100 to convert it into a percentage. So for example, if we were finding the percent of hydrogen in water, we would take the mass contribution of hydrogen. And of course, because there are two hydrogens, that will be 2.02. Now, usually we want to report masses with 4 sig figs, so we should report the average atomic mass of hydrogen to be 1.008 and then times 2, so this would be 2.016 grams divided out by 18.02 grams. That, of course, is the addition of oxygen to water, so this would be the mass contribution of hydrogen compared to the mass of the whole thing multiplied by 100. Now, the percent of oxygen, because there are only 2 elements within this compound, and we can trust that we did our math correctly. So whatever we get as the percent of hydrogen, well, we know the percent of oxygen and hydrogen, because there's only 2 elements, should add up to be 100. So you could take this, subtract it away from 100, respecting the decimal places here, so we wouldn't want to restrict our sig figs with a value, theoretically, that we're coming up with from our heads. But you could, subtract away the percentage of hydrogen to get the percentage of oxygen. Or we could, of course, go ahead and find what this percentage is, and then add these, and they should be very close to 100, keeping in mind we rounded for significant figures. Okay, so if we dig into a problem, this is asking us to find the mass percent of carbon in ibuprofen. So we only have to find one value. So the percent of carbon here, we would need 13 times the average atomic mass of carbon, which would be 156.13 grams, divided out, and nice, the problem actually gives us the molar mass of the ibuprofen. And multiplying by 100, so we're dividing, so we know this will not limit our sig figs. We need to report 5 significant figures, and the correct answer here would be 75.685%, and we absolutely should identify percent of what. So officially, it's carbon in ibuprofen, but that would be sufficient as your answer. That is it. If the problem asked to find the percent composition of ibuprofen, so it didn't specify an element, just percent comp of the compound, we would be expected to find the percentage of each element. So we would have 3 answers. Okay, moving onward. So now looking at empirical and molecular formulas. An empirical formula is often referred to as the simplest formula. An empirical formula is recognized because your elements are in their smallest whole number ratio. This is methane. We don't have to worry about how to name it. This is an organic molecule. This is an empirical formula. However, hexane, which is the main component in gasoline, this is a molecular formula. do you see we could reduce these subscripts down by a factor of 2, and that would give us C3H7. These are not the same compound. Different numbers of different elements yield different particle attractions, which are going to deliver different physical properties. They're different compounds. So even though we have the relationship that this empirical formula, we couldn't reduce down these any further, if we double the subscripts, then we get the molecular formula, but they are different compounds. Ionic compounds, the grand overwhelming majority of the time, are going to be in empirical form. So it's mainly covalent substances that we find possibly in molecular formulas. All right, so first, the stereotypical empirical formula problem starts by identifying what elements are there by their percent composition. And most times, you're going to just problem solve in the order of the elements as they're given. All right, now, we're after the empirical formula that is made of a compound composed of carbon, hydrogen, oxygen, and nitrogen. Now, remember from an earlier video, we talked about that these subscripts do represent the number of atoms of each element. Well, that would be if you had one molecule. So, practically, we're usually after 1 mole of our compound. So if we can find how many moles in comparison to each other each element has, we have the formula. So that's what we're after. How do we take these percent composition data and then determine the simplest formula from it? All right, our drive is to get moles. Fundamental heart of chemistry. So, the first step I would take is make an assumption that will help simplify our math. If we assume we have 100 grams of this compound, well then we'll have 56.76 grams of carbon, 6.56 grams of hydrogen, and so on. Now you can assume any sample size, but let's make our numbers easy on us. Then we don't have to move any decimal places and so on. So we're going to start out with 56.76 grams of carbon, 6.56 grams of hydrogen, 28.37 grams of oxygen, and 8.28 grams of nitrogen. Well, you already know, don't you, ladies and gentlemen, that if we have mass using average atomic mass values, we can, of course, get moles. So dividing out by 12.01 for carbon, and then this has 3 sig figs, so I'm okay to go ahead and use 1.01, and oxygen 16, and then our nitrogen 14.01. All right, and we want to get our answers obeying significant figures, of course, and we will calculate this to be 4.726 moles of carbon. This is 6.50 moles of hydrogen. Then we have 1.773 moles of oxygen and 0.591 moles of nitrogen. All right, what next? All right, well, we have our moles as they appear per this given information. Where do we go next? Well, we know that subscripts are usually small whole numbers. These values are not whole numbers. Let's force them to be. So let's choose our smallest amount of moles, and let's force this to be 1. And the way that we can do that mathematically is if we divide by 0.591. Then, of course, we'll have 1. And so what we're going to do is say, okay, what if this represented 1 mole of nitrogen? Well then, how many moles of the other elements would we have in comparison? So you choose your smallest amount and divide each by that. still obeying significant figures. And what we get here is 7 point, oh, this would actually round to 8.00, and we get 11.0, we get 3.00. Look at that! And these, of course, can be written then as our subscripts. Now, a problem that you've been given in your textbook or your instructor has given you, your numbers are going to work out beautifully as either whole numbers and a half, whole numbers and a third, or whole numbers and 2/3. And we'll go over those exceptions in a moment. You will not have to liberally round these. They may differ by maybe 2/100ths. So 7.97 can definitely be rounded up to 8. You won't get something like 7.82 and have to round that. So these then are the subscripts, and the answer here is C8, H11, O3, N. That is your final answer. And these are in the lowest whole number ratio. All right. Well, let's just imagine that you're looking at a compound and it's composed of just carbon and... no, I'm just going to give us just a thought example. So let's do carbon and nitrogen. Okay. So what if whenever you got to this point, so you divided by your smallest amount of moles and you ended up with 1 mole of carbon, but then 1.50 moles of nitrogen, or 1.48 up to 1.52. Okay, well, we would never write these as our subscripts. That's just silly. So what you do is you multiply through by a digit all of your subscripts until these get transformed into whole number ratios. So let's try 2, C2N3, still an empirical formula. What if, whenever you divided by your smallest amount of moles, okay, you got 1 mole of carbon, but then you got 1 1/3 mole of nitrogen. And again, it'll be like 1.32, 1.34. So we would not write 1.33 as our subscript. So you're going to multiply through. Multiplying through by 2 will not get this to be a whole number. But what if we multiply through by 3? Then we'll get C3N4, still an empirical formula. What if it would be 1 2/3? Well, there again, you would multiply through. Multiplying through by 2 will not make these whole numbers. But how about 3? So C3N, just be careful, that would be 5. Still an empirical formula. All right. Well, what about this? Let's see. Starting out with this example, it sure does start to look just like the problem we did before. Oh, but we're given a molar mass, and then we're asked for the molecular formula. All right, so we have to keep this in mind. But how we attack this problem is first finding the empirical formula. So we're going to do the same thing we did, and that would be to go ahead and make the assumption of 100 grams of sample. So we would have 49.48 grams of carbon, 5.15 grams of hydrogen, 28.87 grams of nitrogen, and 16.49 grams of oxygen. What do we do now? Get to moles, dividing out by average atomic mass. All right, so I'm just going to do that for carbon, but I know that you could just go ahead and do the other conversions for the other elements. So what we end up getting is 4.120 moles of carbon. We get 5.10 moles of hydrogen. It would be 2.061 moles of nitrogen and 1.031 moles of oxygen. The next step, please, please be on guard, because this next step is the main error that students make because they forget to do this. We want to choose our smallest amount of moles, which is oxygen, and divide each by that. Do not forget that step, ladies and gentlemen. Okay, and then what we have is 3.996 4, 4.96 definitely goes to 5, 1.999, 2, and then 1, of course. Okay, so notice smallest whole number ratio. This is our empirical formula. If it asked for empirical, we'd be done, but we need the molecular. The molecular is some multiple of the empirical. So what we have to find out is the molecular formula twice this, or 3 times, or 4 times? Here's how we do it. All right. You were given the molar mass of the molecular formula. So what we need to do is find the empirical formula mass. And so you add up 4 carbons, 5 hydrogen, 2 nitrogen, and 1 oxygen. And for this compound, it is 97.11 gram per mole. Then what we do is take the molecular formula mass, okay, that's of the big multiple, and divide that by the empirical formula mass, and then we'll find the multiple that we need. And then, don't you know, that's 2. Now these may cause a little bit more liberal rounding than these will, to get, whole numbers or whole numbers and a half, whole numbers and a third, whole numbers and 2/3. It's just by the nature of usually the given information that we have. But what we'll do is take all of these subscripts and double them. So the molecular formula will then be C8, H10, and 4O2. There is an additional problem here with the given answers. This is asking for empirical and then molecular. So completing this will be a nice review. Best of luck.